This is the Doppler effect tutorial presented by the SA Charles VB. Hello, welcome to a new tutorial presented by the SA Charles VB. This tutorial we're going to see Doppler effect. And to start with, we're going to have an introduction. If you are on the roadside, you will realize that anytime a car which have a certain sound, which emits a certain sound from it, is moving away from you, you realize that the quality of the sound will depreciate. And if you have a very keen ear, you are going to realize too that the quality of sound depreciates and the pitch of that sound is reducing the more the car speed is increasing and going further from you. Similarly, when a car which is emitting a certain sound is coming towards you with a very high speed, you still realize that the quality of that sound is going to reduce. And still, if you have a keen ear, you realize that the pitch in this case, when the car comes close to you, is going to increase. So this is what happens with the Doppler effect. So we are going to explain this effect now mathematically and even qualitatively. So now, definition of terms: Doppler effect. This refers to a change in pitch when the source and the observer move with respect to each other. The observer is said to move again with respect to source because the frequency can change when the source is stationary and the observer is moving. So if you are moving and the car which emits the sound is stationary, you can also realize the depreciation of that particular sound. With you, the frequency or the pitch will always increase when the source and the observer, the car which emits the sound and you, are always closer to each other. When you are closer to each other, the frequency is going to increase. You're going to realize that the pitch of that sound is going to be higher. But when you are going to be further from the source emitting the sound wave, you realize that the frequency is always going to, or the pitch is always going to depreciate or reduce. So now let's come now to the source. What is the source? The source refers to the entity or body which emits sound waves. Observer. What's the observer? The observer is the entity which receives the sound wave, you in the introduction that you have taken, and the source is a car in the introduction that you have taken. So now let's visualize the principles of Doppler effect. The principle of Doppler effect, we have four main cases in which Doppler effect can occur. And the principle of Doppler effect states that either there will be a change in wavelength or frequency provided that the source and the observer move with respect to each other. So the principle of Doppler effect states that there will either a change in the wavelength or frequency provided that the source and the observer move with respect to each other. So now there are four main cases of Doppler effect that we are going to see. The first two cases are the common ones: the moving source and the stationary observer. The second case is going to be the moving source and the moving observer and the stationary source. The third case is going to be the opposite movement of the source and observer. This one is not well known at times. I'm going to explain it in the latter section. So the opposite movement of the source and the observer is going to be shown here. We have the source and the observer moving in the same direction. And lastly, number 4, we're going to have source and observer moving in the same direction. And this is going to vary due to the relative speed between the observer and the source. So as we're going to see in the latter section. So now, let's say that a source is moving. Let's consider the first case: moving source and stationary observer. In this case of moving source and stationary observer, the principle of Doppler effect that we're going to use is the change in the wavelength. So when the source moves with respect to the observer, we should realize that there's going to be a change in wavelength. So this now is going to be divided into two main cases: when the source is coming toward the stationary observer and when the source is moving away from the stationary observer. So in this case, the first case is when the source comes toward this observer, and the second case is when the source moves away from this observer. So the diagram here is going to show us that when you come closer to observer, the frequency is higher. So we realize that what the wavelength is going to be low, since frequency is inversely proportional to wavelength. So since the frequency as it's coming here closer to the observer is going to be high, we realize that the wavelength is going to be low. And now as the source comes toward the observer, you see that the wavelength is going to be low, and the principle of the moving source with stationary observer is that there is a change in wavelength and not a change in frequency. So now we are going to use now this formula. We say that the lambda which is observed or which is perceived by the observer is going to be equal to the lambda of the source minus delta lambda. It is minus here because we realize that the lambda or the wavelength, it is lower than the wavelength produced by the source. So as it comes here, you will realize that this wavelength is going to be lower. So here you have lambda 0 is equal to lambda minus delta lambda. But we know that lambda 0 is going to be given as the speed of sound in air all over the frequency observed, while the lambda is going to be equal to the speed of sound in air all over the frequency of the source. So, and also the lambda, the delta lambda is going to be due to the speed of the source. So it's going to be equal to the speed of the source divided by the frequency of the source. When you substitute all this, you have c all over f0 is equal to c all over fs minus vs all over fs. Now calculating all this, you realize that the f0 or the frequency observed is going to be equal to c all over c minus vs all into fs. So realize that there's a negative sign on the numerator, on the denominator here, for a source which is moving closer to an observer. So when a source is moving closer to an observer, there's a negative sign here, and this is because you require the frequency f0 to increase. So see, when there's a negative sign here, the higher the velocity, you see that the higher the velocity, the lower will be the denominator, and since the denominator is going to be lower, it implies that the f0 is going to be higher, or the frequency that is going to be observed. So this is why in the case of the introduction, we said that when a car emitting a certain sound is coming closer to you with a high speed, then you perceive that sound to be with a higher frequency. This is because of this formula here. Now when the car now is moving away from you, so the source is moving away from the stationary observer. So in this case now, what's going to happen? You see from this diagram that as the source is moving away from the observer, the lambda is going to be, the wavelength is going to be higher. Since the wavelength is going to be higher, then we are going to use delta 0 to be equal to delta s plus delta lambda. In this case, we are going to use a plus because the wavelength is higher. So now we still know that delta s is going to be c all over fs. Since you know that delta s is c all over fs, you are going to substitute, and we see, and delta f is equal to c all over f0. We substitute all this in this equation, and we are going to end up with a positive sign in this case. So when the source is moving away from the observer, you realize that the denominator is going to have a plus sign with velocity of source here. So this is a formula for the frequency observed, and it is similar to the case, and we realize that what if a car is having a higher velocity and is moving away from a certain observer, the velocity vs is going to be very high, which makes the denominator to be very low. Since the denominator is going to be very low, then the frequency observed will be low. Since it is going to cause the denominator to be very high instead. So since the velocity is high, it implies that the this is going to increase, the denominator is going to increase, and going to cause the frequency observed to be lower. And this is similar to the aspect where the car was moving away from you in the introduction. When a car emitting a certain sound is moving away from you away from you, you realize that that sound, the sound frequency is going to be depreciating. The frequency is going to reduce. Now let's visualize the case of observer and a stationary source. in case where you have an observer and a stationary source, you realize that what it can be here, the principle that is used is the principle of the change in frequency and not the change in wavelength. Change in wavelength is used when you have a moving source and a stationary observer, but when you have moving observer and a stationary source, we use instead change in frequency. This is divided again into two main types. You have observer moving toward a stationary source, and you have observer moving toward observer moving away from a stationary source. So let's take the first case, observer moving toward the stationary source. So when this observer comes towards the source, what do you realize? You realize that the source is going to have a higher frequency. So in this case, you realize that what, since this observer is coming closer, this is going to be more frequent. Why? Since this is going away, this is going to be less frequent. So here you realize that what, the f0 as going to come closer to the source is going to be equal to fs plus delta f. But we know that what, fs is going to be equal to delta f is going to be equal to v0 all over lambda of the source. Here it is v0 all over lambda of the source because the change in frequency is due to the motion of the observer and not the motion of the source. Here the source is stationary. So you are going to have delta f is going to be equal to v0 all over the delta the lambda of the lambda of the source. So we are going to have f0 is going to be fs plus v0 all over delta s all over lambda s. So now fs, now we know that this frequency is going to be equal to the speed of sound all over the wavelength of that sound wave. So we are going to have now f0 is going to be equal to c all over lambda s plus v0 all over lambda s. So when you have all this, but you already know that this again is equal to this. When substituting back, our last formula for frequency observed is going to be f0 is equal to c plus v0 all over c or into fs. So here we realize that what the observer, when the frequency due to the motion of the observer is going to affect the numerator of this formula here, and we realize that since the observer here is coming closer, you have a positive sign for the observer coming closer to a stationary source here. But in the case of the source coming closer to the observer, you instead had a minus sign on the denominator. This is because of the inverse proportion which exists between the numerator and the denominator. So we see that a point to note is that the source is going to affect the denominator of this formula, while the observer's motion is going to affect the numerator of this formula, and all of them are going to be inverse to each other. So now let's visualize the observer moving away from a stationary source. So now if you have since you have the observer moving away from a stationary source, here you are going to have, you see that from this diagram above here, the frequency is going to be lower. Since the frequency is going to be lower, the formula for f0 we are going to use is going to be fs minus delta f. Since we use the fs minus delta f, we can see that delta f is equal to fv0 over lambda. We substitute here, and we know that fs is going to c all over lambda as we substitute again. We are going to have this. The final formula is going to end up as having f0 equals to c minus v0 over c all times fs. So this is the final formula which is observed by the observer, which is perceived by the observer when the observer is moving with respect, and when the observer is moving and coming and going away from the source. So now let's visualize the next section, which is opposite movement of the source and the observer. So example is this diagram here. When the source is moving, when the observer is moving here and the source is moving in the opposite direction, we realize that there are certain formulae you are going to use. So provided that in this case you realize that you are going to use a combination of both the observer moving away from the source and the source moving away from the observer. We realize that here in this diagram the observer is moving from the source and the source is also moving away from the observer. So we are going to use the numerator of the formula where the observer was moving away from the source. So if we can come back, observer moving away from the source, the numerator of that formula was c minus v0. And now we are going to use the denominator of the formula where the source is going to move away from the observer. We come back here, the formula where the source is moving away from the observer. So you have moving observer and source. Here you have source moving away from the stationary observer. In this case, the formula, the denominator was C plus Vs. So now we are going to combine the numerator and the denominator to have the formula when both of them are moving in opposite directions. Source and the observer are moving away from each other. So we are going to have the numerator of the when the observer is moving away, and the denominator when the source is moving away. So it's going to give F0 is equals to C minus V0 all over C plus Vs all into Fs, where V0 here is going to be speed of the observer, and Vs is going to be speed of the source, and C here are going to be speed of sound in air. Fs is going to be the frequency of the source, and F0 is going to be the frequency observed. So now when the source and observer are moving toward each other, we are going to use the formula when the observer is coming closer to the source, and that formula has a numerator of C plus V0. And we are going to use the formula when the source is coming closer to the observer, and that formula has a denominator of C minus Vs. So when we combine them, we are going to have F observed is equals to C plus V0 all over C minus Vs all into Fs. So this is the combined formula for both cases, so when they are coming closer to each other. So now let's go down to the last section, and the last section is going to be source and observer moving in the same direction. So this is the last case that's going to occur, and this case is going to cause the first case, the case here that when the source and observer are moving in opposite direction. Here the principle is that both the wavelength and the frequency are changing with respect to the motion of the source and the observer. Both here the wavelength and the frequency are going to be changing. But now in case of the source and observer moving in the same direction, we have either the frequency or the wavelength that's going to change depending on the relative motion of the source and the observer. So what do we mean by relative motion? So we are going to visualize it in some period from now. So now we need to know that the source and observer moving in the same direction is divided into two main parts. We have the source chasing the observer, and we have the observer chasing the source. So let's start with the first one, the source chasing the observer. So in this case, we have a source coming closer to an observer which is trying to go away. So now this case is going to be divided into two main parts. So if a source is chasing the observer, either the source is going to have a velocity that is going to be greater than the observer, or the observer has a velocity which is greater than the source. So we will see that either the source is going to have a velocity which is greater than the velocity observed, or the observer is going to have a velocity which is greater than the velocity of the source. So now let's take the first case when the velocity of the source is going to be greater than the velocity of the observer. So if the velocity of the source is greater than the velocity of the observer, it is as if the observer is going to be stationary and the source is going to be moving with respect to the observer. So though the observer is moving with a velocity v0 here, we realize that we're taking the relative velocities. We see that since the velocity of the source is going to be greater than the velocity of the observer, we realize that the source is going to come closer to the observer than the observer leaving. So we can consider this motion here with a Vs greater than V0 of being a motion of a moving source coming toward a stationary observer, and the velocity of the source which is going to be taken here is going to be the relative velocity, and that relative velocity is going to be Vs minus V0. The Vs minus V0 is a velocity with which the source approaches the stationary observer. So now this is the formula now that was used in the case of a moving source coming toward a stationary observer was F0 is equal to C minus C all over C minus Vs all into Fs. So we are going to use now this formula in order to calculate this equation. So when using this formula now, we'll substitute down the Vs here in this case as being Vr, and the Vr is going to be V0 minus Vs. Okay, now let's visualize the second case. In the second case here, we have a source chasing the observer. So now, since the source is chasing the observer now, let's say the first case was when the velocity of the source was greater than the velocity of the observer. Here, the source is going to approach the observer, and the observer is going to be taken as being stationary. The velocity which the source is going to approach the observer is going to be Vr, which is going to be equal to Vs minus V0. Now, if the source is chasing the observer with V of the source, this velocity of the observer being greater than the velocity of the source, so we are going to realize that what the observer is going to leave much more than the source come closer to it. So the observer is going to be moving with respect to the stationary, with respect to the source, and the source will be taken as being stationary. So the relative velocity in this case will be equal to V0 minus Vs, while the source is going to be taken as being stationary. So we can consider the motion of a source and a stationary observer. It's the moving observer moving away from a source, a stationary source. So this formula is going to be the F0 is equal to C minus VR all over C into Fs. And here the velocity of observer is going to be taken as a relative velocity, and that relative velocity is going to be equal to V0 minus Vs. So we need to take consideration of the relative motion between the two bodies for you to visualize the source and observer moving in the same direction principle. Now in the next case, you have the observer. The next section, we have the observer chasing the source. When the observer chases the source, either the observer can have a velocity less than the source, or the observer can have a velocity greater than the source. Okay. So now let's say take the first case when the observer is chasing the source with the velocity of the observer being greater than the velocity of the source. If the velocity of the observer is greater than the velocity of the source, you see that the observer will be approaching the source and the source will be leaving. So this will be comparable to this diagram. So this observer is going to approach this stationary source with a relative velocity of being V0 minus Vs. The V0 minus, so this is, you can take now the formula of moving observer toward a stationary source, and this formula is going to be C plus V observer all over C all into Fs. Now the V observed in this case is going to be the relative velocity, and that relative velocity is going to be V0 minus Vs. Now, if the observer is going to chase the source where the source has a greater velocity than the observer, we realize that the source is going to move away from the observer than the observer coming closer to it. So the source is going to move away from the observer with a velocity Vr is equal to Vs minus V0. So now we can consider now the formula for a moving source away from a stationary observer, and the formula for it is going to be F0 is equal to C all over C plus Vs into Fs. Now the velocity of the source now is going to be taken as a relative velocity because the source have a greater velocity than the observer, and the source is considered relatively moving away from the stationary observer. So this is what we use where we use the word relative, the relative motion, and the relative motion is going to be taken again more precisely in relativity chapter. So from here we have finished all the section involved with Doppler's effect, and we have considered why a car emitting sound wave, as it's coming closer to you, you perceive the sound as being increasing in pitch, and as the car is going away from you at a certain velocity, you perceive that sound pitch to be decreasing. So all this explanation can be seen experimentally and via all the other means. So from here we finish the Doppler effect, and we say thanks for your kind attention. Please don't forget to like and subscribe for Science Makers. Thank you.